Okay, so let me start by thanking the organizers for having me here. It's really great to stay in this beautiful countryside of Germany and listening to all these very inspiring talks. So I'll talk about, designing light in an artificial universe made of spins. And so my talk is going to be slightly deviated away from this, say, topological magnons on top of magnetic order. Instead, it's really built from quantum spin liquid. So this work is a theory work, but it's inspired by a lot of collaborations with experimentalists. And in particular, I want to thank my collaborators, including experimentalists Pengcheng Dai and Bing Gao, their group at Rice, and also Thomas Bill and his student at PSI. And on the theory side, I want to thank my collaborators, Andrei Nevedomsky and Alaric Sanders and Claudio Castelnuovo at Cambridge. And also I want to say that actually all the heavy numerics are done mostly just by Alaric. Yeah. Right. So I want to start with a big picture, or that's this idea that has been mentioned in many of these sci-fi works and also popular science books, which is what if we can, say, change the fundamental law of nature. For example, there are many fundamental dimensionless numbers that describe the, say, strength of interactions in our universe. And it's quite remarkable that these numbers are, say, finely adjusted to make possible development of life. Or in other words, if you, for example, change the fine structure constant and so on, then the entire chemistry of the, say, new universe will be entirely different. So it is very interesting to imagine what can we do to achieve this. And so this brings out the topic model today, which is quantum spin ice. And I'll explain this in detail, but the main message is really that it is 3D U1 quantum electrodynamics. And in particular, it has everything that is in QED, including these gapless photons, and also these gapped excitations as electric charges and also magnetic monopoles. So in some sense, this is like the universe with the simplest gauge theory in a piece of crystal. And our proposal is that in a class of this quantum spin ice material called dipolar octapolar quantum spin ice, which I will explain later, it is actually very simple to experimentally tune or control the quantum dynamics of this emergent QED. And by simple, I mean you just need to turn on external field in the correct direction with the correct amplitude. And this will generate new lattice QED phases and phase transitions. And also you have some very accurate control of the photon dynamics, including you can tune the emergent speed of light, you can have birefringence and nonlinear photon couplings and so on. Right. So before we get there, I'd like to introduce some basics about classical spin ice and quantum spin ice. So classical spin ice is essentially a realization of electrostatics, that is just having the electric field, emergent electric field on the lattice, and it is described by this charge-free condition at low energy. So this classical spin ice is defined on the parachlor lattice, where you have the spins pointing either in or out of this tetrahedron. And the Hamiltonian written in this local z basis is just antiferromagnetic interactions between the spins. And then you can work out the ground state and excited states of this model. It turns out that even on a single tetrahedron, you already have quite a few degenerate ground states. And the ground state condition is you have two spins pointing in, two spins pointing out. So this two in, two out rule is also called ice rule because that's how hydrogen arrange them close or far from protons in water ice. But now if you think of these little spins or little arrows as, say, emergent electric field, then you see that this two in, two out rule maps exactly to a divergence-free condition on this emergent electric field. And then when you have higher energy states or excited states, you will violate this two in, two out rule, which means effectively you have some, say, electric charges on the lattice. Okay, so overall, you have actually exponentially many ground states, exponentially in the system size, because you can often find these loops that goes head to tail, and if you flip this loop, you still satisfy the two in, two out condition, so you are going from one classical ground state to another. And if you flip one spin, then you effectively create a pair of positive electric charge and negative one. So these are the two charge states as your excited states. Now, so in the beginning, people like to interpret this as instead of electric field and charge. In the beginning, it was interpreted as magnetic field and magnetic monopole. So effectively, you have this emergent magnetic monopole in the system, which is a really cool story. And as Martin just introduced us, you can use neutron scattering to measure the spin-spin correlation. And in particular, this divergence-free condition on the low energy sector translates to the fact that this EI-EJ correlator has to obey this projector form, and which shows up as this pinch point pattern. And this is exactly what the static neutron scattering measurements see in these different neutron flipping or non-flipping channels. Yeah. So now let's add quantum dynamics on top of this classical model and see what happens. So what you can do is, for example, add this S plus S minus terms. Then it will, say, flip two spins on top of, for example, a classical ground state and create a pair of charges. So effectively, this is really adding this charge creation and annihilation or charge hopping terms, sandwiched by this by the gauge field term, because you have to, the low energy theory has to be gauge invariant in the end. By doing so, originally you have this degenerate classical ground states, but once you turn on the quantum dynamics, they are not the eigenstates anymore. Instead, you have to basically recombine these states to write down some complicated wave function. And now you have a spectrum. And in particular, on the low energy sector, you have gapless photons and also visons, which are effectively magnetic charges in this language. And on the higher energy sector, you have this two electric charge spectrum, or in other words, it's a two spin-down continuum. What is particularly important is that when you apply these S plus S minus terms, you generate a pair of electric charge, and you can, propagate them around this, say, smallest loop on the lattice. So you can generate these, say, matrix elements that takes a loop going clockwise and flip them to the counterclockwise. So effectively, because this doesn't generate any charge on the lattice, it's effectively this cosine B term, where B is the emergent magnetic field. Yeah? And now your classical ground states is then equipped with this perturbatively generated dynamics. And as a consequence, you have this spectrum of photons and bosons. In particular, the ground state is very well approximated by a superposition of just this classical ice states with equal weight. And then, of course, you have other states in this sub-Hilbert space which forms these photons. And also, now these two charge states, originally degenerate, becomes dispersive because you have these charge hopping terms. So the overall picture is quantum spin ice is a, say, full-fledged lattice emergent QED, has photons, electric charges, and magnetic monopoles. So it's generally very hard to solve this model exactly, except when you add some extra terms. So usually people will need to use mean field theory, quantum Monte Carlo, or other methods numerically to identify what exactly do this spectrum look like. For example, there were some analytics and also semi-classical simulations to identify the photon spectrum in the low energy sector, and indeed we see these linearly dispersing photons. And okay, so now on this electric charge or spin-down sector, before we go there, one thing important is that this cosine B term that are generated perturbatively can either has a minus sign in front of it or plus sign. But your Hamiltonian or your system want to choose a background B configuration to minimize this plus or minus cosine B, right? So then you actually have two different quantum phases. The first one is just B is 0 on each plaquette, which is the most conventional one. And then the other one is you have B equals pi on every plaquette, which is a pi flux phase. You can think of the ground state wave function as having a minus sign or a pi flux between this left going loop and the right going loop when you write it as a cat state. Yeah? So it turns out that this background flux is quite important when you want to compute the two spin-down spectrum or the spectrum of electric charges. And in particular, for the zero flux phase, you have essentially one broad continuum. But in the pi flux phase, you have three, where the third one is a bit weaker. But you have three, and they are more or less flat and separated. So experimentally, people can use dynamical neutron scattering with both momentum resolution and energy resolution if you have single crystals. And people use this neutron scattering to try to see if these spectra are really there. For example, in this material praseodymium hafnate, what we see is that at low energy sector, we do see this pinch point lag pattern. And then at higher energy sector, this is a figure in the xy axis is the momentum space or wave vectors, and the fake color plot is the neutron intensity. We see effectively one more or less flat continuum with this six-legged C-star pattern. And this is consistent with the prediction of zero flux quantum spin ice. Of course, there are always some other possibilities that you cannot entirely rule out, but at least this evidence is somewhat strong support of this material, is hosting a quantum spin nice phase. In another material, cerium stannate, what we see is this Q-integrated density of state, again measured by neutrons. And in this case, we see 3 strong peaks in the dimension of energy or frequency. And this is consistent with the prediction of a pi flux phase quantum spin nice. Yeah? And of course, we also have some other evidences pointing this material to the phase of pi flux quantum spin nice. So yeah, even if you are looking at this quantum spin nice, there are some candidate materials that may realize this very exotic phase. Now, if we zoom out, I think the most important point is that quantum spin nice is an emergent QED. And as a lattice QED, it allows you to probe quantum electrodynamics that are not accessible in our fundamental universe. For example, the electric charges or spinons actually propagate or can propagate faster than the photons, so which is not possible when you have Lorentz invariance, right? Or when you have relativity. So, so you will have this, for example, Cherenkov radiation effect coming from the spinons. Another very interesting point pointed out by Roderick Mossener and Chris Laumann and their group is that the emergent fine structure constant of quantum spin nice is something around 0.1, and this is 10 times larger than the vacuum QED. Yeah, so that means with quantum spin nice, you can also probe quantum electrodynamics that is in a, say, stronger or strongly interacting regime. Okay, so now coming to our work in collaboration again with Alexanders, Claudio, and Andre. So generally, given one particular material, all these spin-spin couplings, JZZ, J plus minus, are fixed. So for one material, you have one version of QED, right? Usually, it is very difficult to control the dynamics of these models. One thing, or the easiest way to add some, say, additional terms in the Hamiltonian is to just introduce an external magnetic field. And here I use big B to denote it, to distinguish from the small b, which is the emergent magnetic field that flip a loop of spins. However, in this conventional dipolar spin nice, in this external field just simply couples to all the 3 components of your spin uniformly. And then you will find it actually doesn't help so much with tuning the dynamics of QED. And the reason is that if you look at this 2-in, 2-out ground states, although it's 2-in, 2-out in the local basis, they actually have different global magnetization. So as you turn on the external field, you introduce this, say, Zeeman coupling that actually lift the degeneracy of these ground states, so they are separated away. This actually works against these loop flipping terms that try to generate, say, matrix elements between these different classical ground states. And now the external field B simply make all these different classical states, separate them in energy. So instead, it tries to drive the system into some magnetic order in general. Of course, for a small b, say smaller than the scale of this J ring, which is J plus minus cube divided by GZ square, you can still remain in the quantum spin nice phase. However, this number is actually very small, so I'd say your system gets driven out of quantum spin nice phase fairly quickly. So what we propose is that the story becomes different quite significantly in this dipolar-octopolar quantum spin ice. It's a new class of these quantum spin ice materials. And in this particular class of materials, you can have accurate control of the quantum spin ice dynamics. So how does that happen? Okay, so in this dipolar-octopolar paracolor spin material, what happens is the ground state pseudo spin half is not made of real spin half. Instead, it is made of this mj equals plus minus 3/2, say, bigger spins. Yeah. So as a consequence, when you look at how it behaves under, say, the lattice symmetry, it is different from a real spin half. And this has been discussed in quite a lot of detail in this paper. But for us, the really important thing is that this SY operator here has the symmetry of octopole, hence the name dipolar-octopolar quantum spin ice. And an octopole does not couple to applied external field directly because it's an octopole and the magnetic field is dipole, right? So they cannot couple bilinearly. As a consequence, the symmetry allowed Hamiltonian just has this seemingly innocent change where you just don't have the local SY coupled to the external field B. Compare, say, to the original dipolar spin ice model. But there are some quite non-trivial physical consequences. So let's think about a classical limit where this Jy is dominant. Okay, so my ground state is this 2 in, 2 out classical states. However, they are not in the local Z axis. They are in the local Y axis. And if I look at this Hamiltonian, now let's do a, say, change of notation. I turn Sy to sigma Z, so the notation is easier to understand. And then I see that the external field B only coupled to sigma X. So what happens now is that this term here does not lift the degeneracy of the classical ground states anymore based on the, say, overall polarization, global polarization of the ground state. Instead, it really only introduces a transverse field in the eyes of the Ising component. So now, once you have this term, what happens is when you generate this loop flipping term, which is the most important term in controlling the photon dynamics, you have this additional process of flipping just one spin, and by this introduced by this B sigma X term. So then your loop flipping term's coefficient is modified or controlled by the external field B. And in particular, because B has a direction, and see here you have 4 different plaquettes facing 4 different directions. So this loop tunneling term on the 4 different plaquettes can pick up different coefficients. And let's say these coefficients are GR, and R labels the different plaquettes. At leading order, the correction is like this, where Z is the, say, unit vector orthogonal to your plaquette. So now you can look at this and try to put B in different direction and see how does this cosine B's coefficient change. For example, if your external field is in global 1, 0, 0 direction, then all the loop flipping terms get modified uniformly, even though they point toward different directions. So the first consequence is that this GB, plotted in color here, can change its value. Okay. So because this is essentially the photon dynamics, this is telling you that the emergent speed of light can be changed. More importantly, you actually have 2 different phases, 0 flux and pi flux, depending on the sign of cosine B. So now you are able to turn on the external field, actually, I should swap pi and 0, sorry. If you turn on the external field, you can drive your system from a pi flux phase up into a 0 flux phase. And so I believe this is the first time people pointing out this kind of possibility of having this phase transition of different emergent QED by this very simple experimental technique. Now, if you put your external field B in other directions, you have the richer phenomenon. For example, for B in 1, 1, 0, you can modify actually 2 of the plaquettes. Well, the other 2 plaquettes don't change. So the first consequence is now you have birefringence. The dispersions of photons, the photons are originally degenerate in its 2 polarizations. But now, because of the, say, propagation speed is anisotropic, these 2 polarizations of photons will have different, say, emergent speed of light. And this is, or different fraction rate, right? So this is exactly birefringence that also appears in classical optics. And more importantly, you also have a new QED phase of this pi 0, 0 flux where you want to have a background of B being pi in 2 of the plaquettes and 0 in the other 2 plaquettes. So you have new QED phases that can be controlled by the external field too. So because of time, I don't have time. I cannot go into details of all of this. But the point is, if you point B in other directions, you can have this frustrated flux configuration where the flux on each plaquette is not quantized to be pi or 0 anymore. Instead, they can change continuously, as shown in the curves here, at least in the large S limit. So this is a bit hard to confirm numerically, I have to say. But what's interesting here is that you actually will have this three photon coupling effects, which also shows up as these steps of your photon. Okay, so to look back, what happens is for this kind of materials, you really just need to introduce a small external magnetic field in the right direction, and then you can have a rich variety of tunable QED dynamics, like changing the speed of light, new quantum phases, and birefringence, and so on. Yeah. So the calculations here are done by in this large N semi-classical dynamics and analytical calculation, but we also have done 72-site ED constrained to the 2-in, 2-out sub-Hilbert space to test all these results carries over. Right, and finally, in terms of experiments, there are on the market 3 cerium compounds that are this dipolar-octopolar quantum spin ice, or at least dipolar-octopolar parachlor spin systems. So according to a recent paper by Yang-Baek Kim's group, it seems like for these 3 materials, by turning on the external field, they don't really go into this interesting new QED phases, but well, you can be hopeful that there are some materials that are sitting at the right parameter regime where you have these interesting phase transitions. Right, so yeah, to summarize, you have quantum spin ice as a mini universe of QED, and now for this class of a material, you can tune the dynamics quite flexibly. Yeah, and yeah, for the last slide, we're organizing a generalized symmetry workshop in Okinawa, Japan. So if you're interested, you can take a look. Okay, thank you.
All right, thank you very much.